Welcome to ECE 302. This is lecture 2.1 on set theory. I am Professor Stanley Chan. So here is the outline for today's lecture. We are in section 2.1 of our course. And as you can see in this outline, we have 8 subsections for this lecture. I will spend the first 3 subsections on some basic notations on set theory that includes sets, subsets, empty sets, and universal sets. And then I will talk about union and intersection. And afterwards, I will introduce some additional set operations. What is a set? A set is really a collection of objects. We denote A as a set that contains many different elements. So you can see that in this notation, this set A will contain elements psi 1 through psi n. And each psi I is an element inside this set. Now I want to introduce some notations for the set. If I write this notation here, I mean that an object psi is in the set A. If I put a stroke that go across this notation, then I mean that this element psi is not in the set A. There are different types of sets. We can have a finite set which contains a finite number of elements. For example, here, this set A contains 2 elements. The first element is 0, the second element is 1. A set can also be countable. It doesn't need to be finite. Here, this example shows that I have a set which contains elements 2, 4, 6, 8, and so on. This is a set of all the even integers. It is not a finite set because this sequence can go to infinity. However, it is a countable set. I can also have uncountable set. In this case, a set can denote an interval. So this notation means that I am looking at elements x with a condition that this x is sitting between numbers 0 and 1. Now I also want to introduce 2 shorthand notations. I'm going to introduce open sets. These open sets, they are denoted by this bracket, and then you can see that it is an open interval on the real line, and you can have open-ended from A to B. So this is what we mean by an open interval. Now I can also introduce a closed interval, and in this case I will have A and B. Once I introduce this closed interval, you can see that there is an equality sign here, right? And therefore that interval, it will include the endpoints A and B. A set is not limited to just containing numbers. A set can contain other things. A set can contain sets. A set can contain real numbers. A set can contain vectors. A set can even contain functions. In these 2 plots, I'm showing you a set of functions. On the left-hand side, I'm showing you a set of all straight lines. Okay, and you can see that I'm just picking random slopes and random y-intercepts, and then I can construct a set of all the straight lines. Here is the set of all the cosine functions with a random phase. What I mean is that you plot a cosine function. Here is a cosine function where you have a carrier frequency omega times t plus some random phase. So here is the phase, and then this phase can be any kinds of number, so it could be a random number, and therefore this set would contain all the possible cosine functions of different phase. If you're curious what is this, the left-hand side, this set of all the straight lines, this is a set of all the functions of the form ax plus b, where I am just choosing a different a and different b, then I will be able to get a different set of lines. And therefore, this is a set of all the straight lines, and here is the set of all the cosine functions. And you can see that a set can contain not just numbers, but a set can also contain functions. A set is a general object, and inside a set we can define a thing called the subset. A subset is really a subcollection of objects in A, and we are going to write this notation B with this notation meaning that all the elements in B is also an element in A. Now there's a small difference between this notation and this. Here it means that the set B can also be a set A, and here it means that B is completely inside the set A. Okay, so if you are wondering how we can come up with this notation, think of the inequality. So here it will be less than or equals to, here it will be strictly less than. If you have a set B which is completely inside A, then we say that B is a proper subset of A. So here is an example. Suppose that A contains 6 numbers, 1 through 6. B contains 2 numbers, 1 and 2. Then clearly B is a proper subset of A because all the elements in A is an element in all the elements in B are elements in A. The other example would be that if you get a set A which contains 3 elements and B also contains these 3 elements, then you can say that B is an improper subset of A because for any element that's in B is also in A. However, B can also be equal to A. Okay, so here I'm giving you a proper subset, and here I'm giving you an improper subset. As you can see that it's very easy to show results in a set theory if you are able to draw a diagram. Here is just one example of the many theorems that we can prove. Suppose that you have set A and set B. A is an improper subset of B, and B is an improper subset of A. Then A has to be equal to B. Now, if you draw the diagram, you can see that here is the entire space, and then you have one set, and then now this is your A, and here you want A is completely inside B. Okay, so this is the meaning of A being a subset of B. It has to be completely inside, or it can equal to B. So here you have a B. Okay, now if you only have just one statement, then you're all good. But now you have 2 statements, which says that this B, this is your A. Okay, so this is your B. And now the second statement says that B has to be also in A. Now to make this happen, A has to be like this shape. So in what situation can these 2 be identical? Well, if these 2 has to be happening at the same time, then the only possibility is that B has to be equal to A. So what happens is that you draw an A here, and then you draw a B right on top of that. That is your B. When they are exactly the same, then of course you will have A in B and B in A. Now here is a very simple proof of this result. It's just a sequence of logical arguments, and so suppose A is completely inside B, is a proper subset of B, which means that A doesn't equal to B, or you may consider the other case where B is completely inside A, okay, which doesn't really matter in our proof. Then, according to this definition, you will be able to find a B, X index in B, but not in A, because A is a subset of B, right? So therefore, you should be able to find some X, so this is your X, which is in B, but is not in A. Okay. However, because you have the other requirement that B is completely inside A, that requires that X is also for all the X that's in B, it has to also be in A, and therefore you're reaching a contradiction. The contradiction is between that you say that X cannot be in A, and then now you say that X has to be in A. So there's a contradiction, and the way to remove this contradiction is to make this A equals to B. Okay, so you see that the proof of this set operations is just a sequence of logical flows. Once you draw the diagram, it should be pretty straightforward to see in the relationships. There are two additional sets that I want to introduce. One is called the empty set. And so we say that a set is empty when it contains no element. And we're going to use this notation a 0 with a stroke then to denote an empty set. And then the other one would be called the universal set. In this universal set, I'm going to use this notation omega. Okay, so omega will contain everything you have, and inside this omega you can have set A, set B, and so on. Okay, so this is a very brief introduction of the basic set theory, and then what we are going to do is to introduce several operations of the sets. One is the union, the other one is the intersection. So let me first talk about finite union. So suppose I have two sets, A and B, and now I want to consider a thing called a finite union. This union has a notation U. Okay, so you write A union B. Now, how do you see this? Well, the easiest way to see this is to draw a diagram where you have a set A, and then you have a set B. Then the union will be it will be all the elements that is in A or is in B. Okay, so that would be the set that is going across both A and B. So to see how this can work, let's look at an example. Suppose you have a set A which contains 4 elements, 1, 2, 3, and 4. B contains 3 elements, 1, 5, and 6. And so A union B will just be a set that contains everything that's in A and everything that's in B. So that will have a 1, 2, 3, 4, and then you have 5 and 6. Right? Because you pick an element here, it has to be let's say 5. 5 has to be either in A or B. In this case, 5 comes from B. Okay. Now, how about the other example where you have A being a semi-open interval and B is another semi-open interval. So A would be an open interval from 3 to 4, and then B will be an interval from 3.5. Okay, so here is your B, and then here is your A, and then we want to find the union of A and B, and so the union of A and B would be the set that contains everything that's in A and B, and so you can have this. Right, so this is the A union B, and this A union B, of course, it would be the set that goes from 3 all the way to infinity, and so this is A union B would be the set that contains all the t such that t is bigger than 3. Finite unions are usually quite easy to calculate, but in our course, we sometimes need to deal with infinite unions. So what is infinite union? So this infinite union is defined as this notation. You have a sequence of sets, A1 through AN, and then you are taking the union. So this notation, it means union going from n equals to 1 to infinity. You take this infinite union of sets and then you define a limiting object as A. So this infinite union is is the set A such that for any x that is in A, it has to be inside at least one of those A1 through AN. Okay, so it could be a little bit abstract to understand what this means, but let's look at an example which would become clearer. So suppose you have a sequence of sets. These are all the intervals from 0 to 1 minus 1 over n, where n goes from 1 to infinity. And so what are these sets? So you can have A1, this is 0 and 1 minus 1, right? Because 1 over 1, that's 1. Okay, so then you have a set that contains 0 only. Now A2 is a set that is from 1 to 1 minus 1 half. So this is 0 and 1 half. Okay, and then A3 is 0 and 1 minus 1/3, and so you have 0 and 2/3, and so on. Okay, so these are all the sets inside the sequence. And then now I want to take the infinite union. I'm taking the union of all these. Okay, and so now if you want to draw this diagram, you can see that A1 will just be a point. A2 will be from 0 to 1 half. A3 would be from 0 to 2/3. A4 would be from 0 to 3/4, and so on. Right. So these you can see that it's keep going. Okay. Now we ask what will happen in the limit when n goes to infinity. Well, when n goes to infinity, then your set an is actually turning into 0, and then now this is certainly 1. Okay, now the question is, should this be an open bracket, or should this be a closed bracket? Because this last case seems to be the point of the tension. Okay, so if you look at this infinite union, what it says is that if you want to determine whether this point 1, okay, this point 1 will be included in this limiting object A, you want to check whether this number 1 is living in at least one of these finite sets. So you can check. Let's say this is 1, okay, and you can see that here you have a 1. Is 1 living here? Well, the one is actually living outside this set. Okay, so it's not true. Okay, so 1 is not inside A2. And then is 1 living here? No. And is 1 living here? That's also no. Okay, so no matter which n that you pick, that number 1 is never included inside this closed interval, and therefore we say that this one cannot live in the infinite union, and therefore this infinite union, which is the union going from 1 to an, this has to be a semi-open interval that goes from 0 and then all the way to 1, but doesn't include the number 1, and therefore the solution to this problem is this case. Okay, now just to recap, what we have done is that in this infinite union, what you need to check is to look at these limiting points and see whether this limiting point is living in at least one of these ANs. Okay, so let's also talk about finite intersection. The finite intersection is the opposite of the union. In the union, you're taking an OR statement, and in the intersection, we're taking an AND statement. So the diagram is this: you have a set A, and then you have a set B. Here is your A, and then here is your B. Then the intersection will just be anything that is in the middle of both. Okay, so now if you look at the example, it should be pretty straightforward to calculate. Suppose you have set A and then you have set B, then the intersection will just be A intercept B. It will be the set that contains elements that is living in both of the sets, then it can only contain one because one is in both of these two sets. Now, suppose you have this interval problem again, where you're going from 3 to 4. This is your A, and then you have 3.5 and all the way to infinity. Then the set of A intersect B, you can see that it will be this interval. So A intersect B will give you from 3.5 and then all the way to 4, and you have to close at 4. Okay, so this is a set A, this is a set B, and here this is the set of A intercept B. Now we can do the same thing for infinite intersection. The infinite intersection now contains a sequence of sets A1 through AN, and then for an element X to live inside this set A, this X has to be inside all of these finite sets. Okay, so let's look at one example. It will be clearer. So suppose AN is given by this equation, where AN is 0, and then 1 plus 1 over n. So that means A1 will be 0 to 2, and then A2 would be a set that goes from 0 to 1 over 2, and then 3 over 2, and then A3 will be 0, and then 1 plus 1 over 3, so that is 1 plus 1 over 3, so that is 0. Okay, so that is 0 to 4 over 3. Okay, all these, they are open intervals on the right hand side. So now we ask as n goes to infinity, and then this set should look like the following, where you start with a 0, and then you start with 1 plus 1. Okay, and then now if you n goes to 2, it'll be 1 plus 1 half, or 1 plus 1 third, and so on, right? So as n gets bigger and bigger, you are going towards the left hand side. So every time it is an open interval. Okay, and so ultimately what will happen is that you will be getting a set that takes this form, 0 and then 1, because when n goes to infinity, this is going to 0, right? So you have 1. Now the question is whether this is a open interval or whether this is a closed interval. Okay, so ultimately the question still goes to the same issue, is whether this 1 should be included or not. And you can see in this illustration, in any kinds of AN, okay, in any of these ANs, this 1 is always included. Okay, so this is for n equals to 2, n equals to 10, n equals to 100. 1 is inside these sequence of sets. They're always inside. Okay, and therefore, since 1 is always included, then you have to go with this case. Okay, because 1 is included in this limiting object A, and therefore the answer to this problem is this. Okay, so to recap, the difference between infinite intersection and the infinite union is whether your element, this X, has to be inside all these A1 through ANs, or it has to be in at least one of those. So after visiting the subject on union and intersections, let's continue our discussion on other set operations. I'm going to introduce two here. One is on complement, the other one is on difference. And then I will talk about the notion of disjoint and partition of sets. The complement of a set A is the set that contains all the elements that in in omega, but not in A. It would be easy to draw a diagram where you have a omega, and then you have the set A, which contains anything that's inside. And then what is complement? Well, complement is anything that is outside of A. So here it would be A complement. For example, if A is the set of all the integers and omega is the set of all the integers, then A complement would be the set of all the odd integers. Now, pay very attention to this omega. Here I'm defining the omega to be the set of all integers. If omega is the set of real numbers, okay, then A of A complement is not just the set of all the integers. It would be real numbers that are not even. Okay, so that contains what? Well, as long as you don't give me 2, 4, 6, 8, and so on, so you can give me 1.1, you can give me square root 2, you can give me square root 3, and so on. As long as they are not even integers, that could be considered in this A complement. So you cannot just tell what is the A complement. A complement has to be defined on two things. One is A, the other one is your universal set. Okay, before you tell me the universal set, the A complement is undefined. The difference between two sets, some people prefer to write it in A / B. Some people prefer to write it as A minus B. Both are okay. All right. So this is the situation where you draw two sets, A and B. Here is your A. This is your B. And then you want everything that's in A but is not in B. So here is the set. Okay, so if you recall this notation here, it would be the set that contains all the psi is in A, and the psi is not in B. A / B or A minus B, that is also equals to A interset of B complement. Now, why is this true? Well, you can draw a diagram. We draw the A here, and then we draw the B here. So here is your A, here's your B. A is this set. And then now what is B complement? B complement is anything that is not in B. So that's the B complement. And then you can see that there is a small region here that is common in both. Okay, and therefore when you take A and then you take B complement, and when you take intersection, you will be able to get us A / B, which is the difference between A and B. Disjoint sets are very useful because they can help you separate the events or sets into two sets that are not overlapping. So in particular, we want to learn this notion called disjoint set. We say that two sets A and B are disjoint if A intercept B is an empty set. And if you have a collection of sets A1 through AN, we say that this collection is disjoint when every Aij is an empty set when they intersect. So here's a diagram. When you have a set A here, when you have a set B here, when you take the intersection, they don't overlap, then you say that A and B are disjoint. Okay. A set can also be in this way. So A, B, and C, A1, A2, and A3. You take any pair, A1 and A2, they don't intersect. A2 and A3, they don't intersect. And A1 and A3, they don't intersect. Then you say that this connection of sets A, B, and C, A1, 2, and 3, they are disjoint. Another notion is called partition, which is built on top of this concept of disjoint. A partition is always built on the universal set. So you have a universal set here, and then you are going to divide this universal set into segments. Let's say here is your A1 this is A2, A3, and A4, you say that these sets A1, 2, 3, 4, they form a partition when two criteria are satisfied. The first criteria is that they don't overlap, meaning that they are disjoint. Okay, so for example here, they don't overlap in this diagram, so they're okay, right? Now, how about the other one? The other one says that it has to be able to decompose your universal set. It means that when you take the union of everyone, it will give you back the universal set. Okay, for example, if you have a set A that contains 1, 2, 3, 4, 5, and 6, it contains 6 numbers, then let's call this omega. Then you can say A1 equals to 1, 2, and 3, A2 equals to 4, 5, and then A3 equals to 6. Then A1, 2, 3, they will form a partition of the universal set omega, because first of all, they don't overlap, and then secondly, when you take the union, you can get back the universal set. Finally, let's just briefly talk about other set operations that can be built on top of the union, intersection, and complements. And by the way, this union, intersection, and complement, they are called the three elementary set operations. In fact, any set operations can be built by taking the union, intersection, and complement of two or more sets. So here we are going to look at a few very commonly used set operations. They are fairly easy to prove. All you need to do is to just draw a diagram and then write down the logical arguments for each case. For example, the first one is called a commutative property. When you take A intersect B, that's the same as taking the intersection of B and A. Okay, so the order doesn't matter. Same for the union. A union B is the same as B union A. Associative property, it says that when you take A union a bracket B union C, that's the same as A union B and then union C. Okay, so which one to do first, it doesn't matter. Same for the intersection. The third operation is called the distributive property. When you take A intersecting B union C, you can just distribute these operations into two. Here you can have A intersect B, that will give you here, and then you have union, and then A intersect C, so A intersect C. Okay, and you can take the union afterwards. Same for in the case when you take union outside and the intersection inside. So that's called a distributive property. The last one is called the De Morgan's law. This result says that when you have A intersect B, when you take the complement outside, that can be written as A complement union with B complement. Now, if you have A union B, when you take the complement outside, then you can have A complement intersect with B complement. Okay, so these are very straightforward set operations. We need these set operations to define the probabilities. So I hope you can take a look at these set operations. And I know that some of you have learned these before, and so I hope this has served as a review. For those who haven't seen these before, I think this is a very brief introduction of a very deep subject. So if you have any question, I encourage you to send us an email, and then we'll be very happy to help you out.